Welcome to a lesson with Dr. Powell. Let's walk through a little proof of why a number field has a primitive element. So we're going to take the case if we have appended two elements, alpha and beta, in the complex numbers to the rational numbers. Now, the question is there an element L such that if we adjoin it to Q, it would actually be equal to this field right here? So here's a little thought. All right. Now, what if we just look at this extension of just adjoining L? Um, now, the minimal polynomial has degree of this particular extension, and the endomorphisms from Q over L into the complex numbers that fix Q, there's a one-to-one correspondence with the roots of this minimal polynomial. That is, L, they're uniquely and completely determined by which root L goes to in this minimal polynomial. And so there's only exactly one of these that actually fixes L, where L goes to itself. So if QL were equal to this, then all the endomorphisms of this field that fix Q into the complex numbers would, so if you're looking at that, so you take the endomorphisms here, there would actually only be exactly one that would fix L, because these two guys would be the exact same. In particular, if you thought about just any element that you adjoin to here to get you closer to this field right here, like say gamma, there's a minimal polynomial here, and you can think about endomorphisms of this field extension that fix Q adjoined L, and there would be some there, with this degree being greater than one. Assuming that gamma actually does this non-trivially in this extension. And so you would have some endomorphisms right here that would actually extend these, and especially the one that fixes L, meaning there is going to be more than one that actually fixes L in that case. So really all we got to do is try to find an element in this field such that all the endomorphisms of this field extension into the complex numbers, so that all of them do not, that only one of them will fix that element. And then we'd actually have the primitive element, or and that would be what we'd be after. In fact, this is what we do. We take a linear combination of alpha and beta. We just take alpha plus some constant times beta, and we look at that, and we think about endomorphisms that act on this to give us this. If we want this to be fixed, so if we want an endomorphism to fix this guy, then this would be an equality here, and you could solve for C, and you could get something here. So all you have to do is make sure that C is never equal to this for any of the endomorphisms here of this field extension. And there's only finite many things to choose from. So if you just choose something that's not in that finite list, you got a good C, meaning that this will never happen. This will never be equal, except for the case when sigma is actually the identity endomorphism. So we only want one to work, so it needs to be the identity endomorphism. So if you just let C be something different than all of these, then only the identity would actually hold, which would actually give you a primitive element. And we have that because there's only finitely many things to steer clear of. So there's definitely something in there that we can use, and so we're done. So hence we can always find a primitive element. In fact, this is a little constructive as well. It actually kind of gives us a constructive idea of how to create a primitive element. Most elements that you adjoin in this field, at least, randomly, will actually be a primitive element. But specifically, in this particular case, we have a construction. So if this works just with alpha and beta, so we can actually remove the adjoining alpha and beta with an adjoining of some element L. And if you could do that with 2, then you could do it with 3. Then you could do it from 3 down to 2 down to 1, and inductively and so forth, so that any algebraic extension of here in this case of finitely many things can be actually written as just Q adjoined one element. So we have primitive elements for number fields. Thanks for watching.